Hey everybody, in this video we're going to be exploring the topic of concavity. So from section 3.4, if you wanted to use that as a resource, just to point that out. We're going to focus our attention on the second derivative test, SDT, the second derivative test for concavity and locating points of inflection. Let's see how the pen's going to work today. All right, instead of writing points of inflection, it's common practice in the AP world to abbreviate and have POIs. Just make sure you know what it means if you're going to abbreviate. Points of inflection. That is where the graph changes concavity. All right, so we're going to look at some interesting examples in this video since we've already explored the topic of concavity. And I'm also going to pull in something a little bit different too that we're going to connect to later. So you'll see as we get there. All right, we've done our background work. We know that if the second derivative is positive at any c value, the graph of our function is concave up. We know that if the second derivative is negative at any c value on a graph, the graph is concave down. We also know that if the graph, the second derivative changes from positive to negative or vice versa, and the second derivative does not exist or is equal to 0, that we have what we call a point of inflection. So using those ideas in our first example. Okay, what we want to do is we want to find the intervals on which this graph is increasing, or I'm sorry, what we want to do is we want to find the intervals on where this graph is concave up, concave down, and if this graph has any points of inflection. All right, the first thing we're going to want to do is we're going to want to investigate this function. We're going to want to notice that that right here, that the function is defined on all real numbers. That is, there's no replacement for x that would cause us to divide by 0, so that's a good thing. I was just a little suspicious at first because I saw this fraction with the variable in the denominator, and I thought, you know, I really need to investigate to see if there are any vertical asymptotes or points of discontinuity. Okay, well, when in fact, when I look at it a little bit further, this function exists everywhere on every x. All right. In order for us to discuss the topic of concavity and points of inflection, we need to get to the second derivative. Well, that's going to require the first derivative. Okay, just thinking back about how to find that derivative, we would use the quotient rule. And then on that, we would use the quotient rule again, clean it up. And I'm just going to give you guys the second derivative here. Because our focus isn't about using the quotient rule twice. It's about once we get to the second derivative, how do we take the second derivative and answer the questions of concavity and points of inflection. So again, I went from the function to the second derivative. I'm not even going to show the first derivative here because the questions in this video aren't about the first derivative. Okay, so through the simplifying process, we end up with this second derivative. Okay, so what do we do from here? Well, on our number line, just like our f prime number line, let's go ahead and locate zeros of the second derivative and also where the second derivative does not exist. So thinking about this, maybe this would help us organize our work. Let's first figure out where the second derivative, at what x values the second derivative is 0. So what does that look like? Well, set 0 equal to the second derivative. Oh, I wish I wouldn't misbehave. Okay, cross products. I'm going to divide out the 36. And then I think we can see that we're going to have two solutions here, positive, negative 1. Okay, so what that tells us, let's return to some notation that the second derivative at 1 is 0, and the second derivative also at negative 1 is also 0. So what I'm going to do is I'm going to go ahead and come over here and put those values on my number line. So we have 0 second derivatives at those values. All right, let's go ahead and also organize our work and show we're trying to figure out where the second derivative does not exist. Well, like I did here, I'm just going to set the derivative equal to a does not exist situation, 1 over 0, and do cross products. So if things start to disappear, that's what I'm doing. Okay. Cross products. So where is this expression equal to 0? Well, it's never going to be equal to 0. We've already investigated that from the original function here. But your work could show that when you brought in the square root to both sides of the equation, subtract a 3, you have no solutions here, so nothing else belongs on the f double prime number line. So that's all the work we'd have to do to locate where the second derivative of 0 does not exist. Okay, and then up to, from here, it's just test values. So let's do some tests. Negative 2 in the second derivative. That was a negative 2. This factor is going to become positive times a positive number. Notice the denominator will always be a positive number no matter what replacement for x you make. So positive divided by positive, I'm going to have a positive output. So that's greater than 0. Here I'm going to try 0. That's easy. That would be a negative quantity here, negative numerator, positive denominator, so negative here. So now we know where the graph is kind of, you know, concave up and concave down. Oh my goodness. And then I'm going to test maybe positive 2 here. And it looks like that's also going to be a positive output into our second derivative. So it does look like the concavity changes at these two locations right here. So we're ready to take this information right here off this number line and express it the way we're supposed to. So the function f, based on my observations of the second derivative of this function, my function f is concave up on negative infinity to negative 1, and then again from positive 1 to infinity. And we're going to want to say because, and I'm going to abbreviate here, f double prime is positive, greater than 0. The function is concave down on the interval from negative 1 to 1. We want to justify our answers. Oh. Because f double prime is negative. And then also we observe that we do have a point, more than one actually, point of inflection. So f has, I'm going to double up here and say points of inflection, POIs, plural, at the x values of positive, negative 1, because the signs of the second derivative, because f double prime, and I'm just going to put here, changes signs. That'll capture both points of inflection. Changes signs. Okay, so the graph goes from concave up to concave down, back to concave up at these zeros. So we'll put it all together later and produce a graph, but right now we're just focusing on being able to look at some interesting problems here and make sure that we understand how to report our answers. Okay, before I look at example 2 with you guys, I do want to take a moment and look at this F double prime number line. And I think what I'm going to try and do is maybe in a different color, if you just want to kind of watch here. If I had saved some room here, I wish I could kind of erase this, but what I want to do is I want to think about what our knowledge of the second derivative reveals to us about the first derivative. So, for example, if the second derivative is positive, okay, if the rate of change is positive, if the derivative is positive, that tells us that f prime, if I built an f prime number line here, so to speak, okay, at -1 and 1. Now, don't confuse this with the f prime number line that we've been doing traditionally, but if my second derivative is positive, that's telling me that my first derivative, the graph before it, if the slopes are positive to the slope graph, then that tells me that f prime is increasing. If my f double prime values are negative, that tells me the graph before it, the f prime graph, must be, if I have negative rates of change, that the f prime graph must be decreasing. And likewise, again, if the slopes of the second derivative is positive here on this interval, those are slopes to the f prime graph, then this one has to be increasing. And I just want to take a moment and I want to look at the explanation here, the justification on concave up and concave down and POIs. Okay, a graph is concave up on an interval because the second derivative is positive. Okay, but I can also say because that means then that f prime is increasing. And if you think about that for a minute, if the graph f prime is increasing, its slopes are positive, and the slopes to an f prime graph would be denoted f double prime. Okay, look at concave down. A graph is concave down where the second derivative is negative. Okay, well, if the second derivative is negative, that tells us the first derivative is decreasing. So an alternate explanation, and almost a preferable one by College Board, is where is a graph concave down? Well, where f prime is decreasing. Okay. Now, if you're going through this process right here and you're arriving at a second derivative and you're using a second derivative number line, then certainly by all means use the second derivative explanation, justification for why a graph is concave up or down. But I'm kind of getting ready for something later that we're going to see. So I just need you to kind of pay attention to, if the second derivative is positive, that means the first derivative is increasing. Okay. And I know this is gone here, but let's kind of look at it. The f graph has points of inflection. I think this was at x equals 1 and x equals -1, maybe positive -1, because f double prime changes signs. Well, I could also say an alternate example would be, or justification would be, that I have points of inflection because f prime right here changes direction. The f prime graph goes from increasing to decreasing, okay, because f prime changes direction. So that's an alternate example to justify concavity and points of inflection. It changes direction. And if f prime is changing direction, that means the slopes, the f double prime values, have to change positive, negative signs. So I just thought I'd use this opportunity to kind of get us thinking about that, because that is going to come up here pretty quickly soon, and we'll want to kind of build on that at that time. Okay. So I do have one more example. Let me start another video on that one. See you in just a second.